I'm Brandt. I'm a postdoc in Cologne. I want to thank the organizers for giving me a chance to talk about this, some kind of interesting results in modeling that me and my collaborators did this past year. I want to beg forgiveness for anything I might say that might be a bit wrong. I mostly come from the astrochemistry and star formation side, and this was kind of my first foray into radioactive isotopes and protoplanetary disks. So thanks to the great review talk we had, we can kind of say as an observation that the early solar system was at some point somehow enriched with some short-lived radioactive nuclei, such as aluminum-26, iron-60, or beryllium-10, and so on. So a question which was raised in the review talk was, since they are short-lived, how and where was this enriched material produced, and when was it introduced into the solar system? And of course, we saw that there was many different mechanisms with kind of the 7 categories presented in the review article. And this talk will unfortunately add on another category for that. But in general, I kind of see the enrichment as kind of breaking off into 2 different sections myself. One are internal mechanisms, and kind of the most dominant internal mechanism that had been proposed was by T-Tauri stars, which would accelerate particles in the reconnection regions around the stars shown there in the schematic on the left. The cosmic rays would be accelerated in this reconnection ring, which these cosmic rays would then produce aluminum-26, and then that aluminum-26 would then get pushed out into the rest of the disk through an X-wind. This mechanism was somewhat nice because it allowed for a general mechanism, just required a T-Tauri phase to happen, but it would impose a heterogeneity in the distribution of aluminum-26, and this has been kind of a contentious issue of whether or not it's homogeneous or not. Some issues with this is that the cosmic ray flux that would be needed to do this isn't really well supported by the X-ray data. And furthermore, it requires that the enrichment happens in this accretion zone, which is kind of this gap between where you see the disk and the protostar is. And in that accretion zone, there's just not a whole lot of dust to begin with. On the flip side, you have external mechanisms. So I'm showing some really beautiful visualizations of the Fujimoto simulations, where they considered an entire galaxy disk. And they had different sources for aluminum-26 and iron-60. And you see here the distribution of the gas, aluminum-26 and iron-60. And zoomed in, for instance, you see that the aluminum-26 kind of traces the hot gas, but it's kind of spread all out where you see the gas. What they found was that they could reproduce the galactic distributions and the amount of aluminum-26 pretty well, and that it can seed the galactic disk with these short-lived radioactive nuclei. One of the issues is that their simulations, their smallest cell size is 7 parsecs. So their kind of best resolution scale for structures is maybe 14 to 20 parsecs. So they really couldn't resolve the transition from kind of the interstellar medium into the dense cold clouds or into the protostellar cores. And some previous simulations by a postdoc here in Cologne, Daniel Seefried, in 2018 showed that it's actually fairly difficult for a hot feedback gas to mix with the cold, the cold dense gas, especially later on in a cloud's evolution, and that the kind of hot supernova gas, for instance, would just kind of blow around dense protostellar cores that have condensed out of the clouds. So we thought of a different proposition. What if protostars themselves could help produce or fully produce the aluminum-26 just during the star formation process with some form of general mechanism? And this was kind of our hopes and dreams. And so to start with, talk about how this happened. So we consider the acceleration of cosmic rays by protostars, and this is kind of a schematic of the main site of acceleration that we are considering, which is at the accretion shock on the surface of the protostar, which is the kind of blue rings you see denoted there. These accretion shocks are very dense, with densities of 10 to the 10 to 10 to the 12 particles per cubic centimeter, and they're hot. They can get between 500,000 upwards of 1 million degrees Kelvin. So this provides a very good location for cosmic ray acceleration. So in 2018, I modeled the acceleration of cosmic rays in these accretion shocks. So what you see here in the schematic is the cosmic ray spectrum, so the flux on the y-axis, the energy on the x. In this case, this is for a 0.5 solar mass protostar, and then the color just shows the final mass of the protostar. It's not particularly important. And in this case, we assumed a specific accretion history. But what you see is that as the solid line, which are the protons, the accretion shocks are able to accelerate cosmic rays up to around 10 GeV. However, the energies that you need to produce Al-26 are in the MeV range, so it's actually pretty good that it doesn't accelerate things too high. So if we have these cosmic rays accelerating in the accretion shocks, and then they're able to transport into the disk, we thought maybe that can produce Al-26. So this is the kind of generic mechanism that we're proposing here, the model that we use to solve it. So we start a little gas parcel denoted by this little cluster of red points. We started at 1 AU, just kind of arbitrarily, and then we let it free fall in with the accretion. And as it's free falling in, we recalculate the cosmic ray flux at every point along the disk as it's falling in. And the cosmic rays flux, or a spectrum, is then used to calculate the amount of aluminum-26 being produced from the aluminum-27, magnesium-26, and silicon-28 in the disk surface. Then this gas parcel gets accreted, and then we assume some fraction of that is put out into an outflow, and then some other fraction of that falls back on to the disk. And so there's some transfer distance that it falls out into the outer disk, some that it falls into the inner disk, but these kind of things aren't really well parameterized, so we just put it into a factor that we can check later. For the cosmic ray physics, we assume that the cosmic rays are attenuated by some column density from the disk accretion, which is modulated by some factor here, epsilon, and then spatially transported rather than 1 over r squared, which is sometimes used. It's a much steeper relation here where the transport is along a combination of a dipole, quadrupole, and octupole field. So basically, this is what we do is as we evolve a protostar from some low mass up at a constant accretion, we just allow these packets to keep falling through the disk, and then having train material recycled back through the disk. So one of the things we first wanted to check was, well, what if we just have a big burst of accretion? Big accretion bursts have really high densities in the accretion shocks, produce really hot shocks, so we thought maybe this is how we can really do it. So this model we have, it's kind of a very phony burst, but we have a burst of 10 to the minus 4 solar masses per year for 100 years, 10 to the minus 5 for 1,000 years, and so on in kind of logarithmic steps. It's not a real burst, but it's kind of gives a good kind of 0th order check. What we find though is, so this is the y-axis is the ratio of aluminum-26 to 27 with time. The hatched region here shows the ratio of aluminum-26 to 27 measured in different conjugals, and then the dotted line up here shows the kind of canonical rate measured in calcium aluminum rich inclusions. What we find is that it's really high, we actually get no production of aluminum-26 in our gas parcels in the disk. And so these little dots that you see here are the enrichment when the gas parcel has finished free falling in and is about to be accreted. So we find that basically we only get the production of aluminum-26 when the accretion rates go down. So unfortunately, the accretion burst can't really solve it. However, we then decided to try a different model where we just used constant accretion rates. So we considered 4 different constant accretion rates. And so we just evolved the protostar with constant accretion rates. And again, what we find is that for these very high accretion rates, which are in blue, we get very little aluminum-26 production in the disks. For basically all masses that we consider, we can never reproduce a calcium-aluminum rich ratio of aluminum-26 to 27 when you have higher accretion rates. However, once the accretion rate drops below 10 to the minus 8, we suddenly have a significant amount of a significant increase in the amount of aluminum-26 being made in the disk surface. And so in particular, you can look at the red line here. This is for an accretion rate of 10 to the minus 9, which is the accretion rate that you see kind of as a protostar is transitioning from class 1 to a class 2. And that transition region towards class 2 is when it's thought that the disk is able to cool enough for calcium aluminum rich inclusions to start to condense out of the disk. And so we find that for these low accretion rates, we're able to produce either the canonical amount of aluminum-26 or even more within the disk surface. So one thing you might notice is there's a lot of gaps in this plot where the aluminum-26 just, and it turns out this is purely an artifact of the protostellar evolution model. So what I show here is the protostar's radius as a function of mass for different accretion rates. And what you see is that there's different masses in which the radius undergoes kind of a transition and balloons out. And when it balloons out, the accretion shocks become subalfanic, and this dampens the acceleration of cosmic rays. And so one of the most kind of important parameters for these models is the protostellar radius and the protostellar magnetic field. Unfortunately, for class 0s and class 1s, these are two of the most unknown parameters we have for protostars. So that's kind of a big problem in that the two most important parameters for this model, the magnetic field and the radius, are unknowns. This fiducial case also assumes that around 10% of the material being accreted, 1% of the material being accreted is recycled back onto the disk. So you don't need a lot of recycling in order to keep the disk over time enriched. So this is a similar case. So this previous model was for a magnetic field of 1,000 Gauss. Which is kind of what's been observed for class 2s or later protostars. For class 0s and 1s, we don't really know. So we did a model instead with 10 Gauss. And what you find is that the amount of aluminum-26 production is much higher, and that even for accretion rates of 10 to the minus 8, you're able to match or exceed the canonical amount of aluminum-26 in the calcium aluminum rich inclusions. For the very low accretion rates, you're actually overproducing by a factor of 10, but you're overproducing it before the calcium aluminum rich inclusions have really started to condense out. So you still have some kind of wiggle room with the decay time to get back to the measured value. The reason why the magnetic field has this big effect is that when you lower the magnetic field for basically all radii, the accretion shocks stay super alphanic, and so the accretion shocks are more conducive to the acceleration of cosmic rays. So to kind of sum up and conclude, because I'm not sure where I am on time, in situ irradiation by cosmic rays accelerated in the protostellar accretion shocks seems to be a viable mechanism to produce the aluminum-26. We find that, unfortunately, accretion bursts are not a very viable source. Although they do have a high amount of accretion and thus a high amount of energy. The high accretion rate leads to a much larger radius and much more attenuation along the accretion column that the cosmic rays then have to travel through to get to the disk. The model thus requires a low sustained amount of accretion due to the smaller radius and the smaller amount of gas attenuation along the column. However, the fact that you need low accretion makes this a general mechanism, because virtually all protostars undergo these low levels of accretion as they transition from a class 1 to a class 2 system. Our models don't really include much in terms of the disk mixing, and we haven't really looked at other isotopes yet, particularly beryllium-10, to see if we also way overproduce it. But we wanted to propose this model as kind of to get it out there while we continue to try and work on to make sure, just how viable this is when we include more and more complicated physics. Thank you again for allowing me to give this talk.